Hi everyone, my name is Isaac Berry from Berry Science Lab, and today we're going to be talking about point vortices. Okay, so first of all, what's a vortices? Well, what's a vortex? This marker's not in prime condition. Okay, this one sounds like it is. Yeah. Okay, so what's a vortex? Well, informally, you might think of a vortex as an area of a fluid where it kind of spirals into a little point, like a whirlpool. Informally, it kind of continues with that definition. Vorticity is just the curl of the fluid velocity. And so, any region of non-zero vorticity is going to be classified as a vortex. Okay, so what's a point vortex? Interesting. Well, a point vortex is essentially a singularity, like a black hole of vorticity. What it's doing is it's a delta function of vorticity. Now, what is a delta function? Well, the Dirac delta function is a very special function. Okay, that probably doesn't say much. Most of the functions that have names are special. Well, this delta function is equal to the limit as n approaches infinity of fn of x, where fn of x is equal to n e to the minus n x squared. So what that means is it's going to look like a sequence of normal distributions. Something like this, getting thinner and taller over and over and over again, until eventually a visualization of it might look like this. So that's what the delta function is, essentially. Big spike at zero, zero everywhere else. But more formally, it's defined using two properties. Its integral over the entire real line actually, why am I putting x, y? I'm only talking about one dimension right now. Is equal to 1, and its integral over the real line when multiplied by another function is equal to that function evaluated at 0. Okay, so that tells us all about the Dirac delta function. Now, we're not dealing with a 1D fluid. So we're not dealing with the surface of something like this. We're dealing with a 3D fluid and a 2D boundary. So this is not going to cut it. We are going to need something more to describe the delta function in 2D. Now you can probably already guess the formal properties. It's going to look something like its integral over the entirety of R2 from minus infinity to infinity and from minus infinity to infinity is just equal to 1 again. And, well, this is equal to f of 0, 0. So, its informal definition then is just going to be this, but we're going to have to change it up a little bit. Now, you might ask, where did the pi come from? Well, this integral by itself actually happens to evaluate the pi. For more information, check out the reason why this evaluates to the square root of pi. Oh, I should have put that in there. Doesn't matter. So this is a more reasonable approach because it allows us to set this equal to 1 when f of xy is just the constant function 1, instead of having to add a nasty 1 over pi to this expression. Alright, so we now know what the Dirac delta function is. Now we need to figure out what that has to do with point vortices. Well, the vorticity field given some point vortex can just be described, if our point vortex is currently at AB, then it can just be described as that Dirac delta function will offset by AB. And of course, we're just going to want multiple at some point. Okay, there we go. So now, let's get to the topic of how do point vortices act on each other? Well, a point vortex by itself on the 2D plane is going to induce some amount of velocity, right? So the vorticity is going to cause some velocity to flow. And that's going to be based on the circulation of this guy right here. And that circulation is, well, what we call vortex strength for a point vortex. So then, this fluid velocity induced is going to be that field strength or vortex strength divided by 2 pi multiplied by z, or the unit vector in the z direction, cross, I guess I'll just write it as r, divided by the magnitude squared. Now you'll notice we found the inverse square law. This is ridiculously similar to the inverse square laws concerning gravity or electromagnetism. Well, it's actually more like the field magnitude, and you can kind of see it shining through here. So this kind of looks similar, but it's not really the exact same because this isn't a constant. Okay, so nothing really interesting happens when they're just one point vortex because it can't move itself. The velocity induced is 0 at this point right here. So what we're going to do instead is deal with 2 point vortices. What if we add a second? What's the flow going to look like? Well, they can move each other. They don't have mass, really, so they just move each other with the velocity induced at each point. So let's say before, when there was only one point vortex, let's say at this point, the velocity induced was this much. Then, when you add a second point vortex right here, let's say if that point vortex was alone, it would have induced this much velocity over here at the origin. And so, this is going to move in this direction, this in this direction. I think you can see where we're going here. Now, that means that let's call x1 the location of our first point vortex and x2 the location of our second. x1 dt is going to be the velocity, or the velocity induced by the second point vortex, which is the strength of the second point vortex divided by 2 pi multiplied by z cross x2 minus x1 divided by the magnitude of x2 minus x1 squared. The x2 dt is the opposite. And notice, of course, that these two quantities are the exact same, but these two are different. All right, so now how can we solve for the equations of motion based on this? Well, something probably instantly comes to mind. What happens if we subtract dx2 dt from dx1 dt? Well, that would just be equal to d dt x2 minus x1, which is what? And keep in mind they have a common denominator. Do something like this. And yes, I flipped the sign of this, so I made this x2 minus x1, and in exchange, I made this a negative, well, actually it should be a positive sign after everything goes through. Okay, minus, minus. Think we can come to a compromise. So this is a negative because I took these, flipped them around, and I added a negative on the outside, and this is a negative because, well, we're subtracting them. So, all in all, it becomes a positive. So this is just the added field strengths multiplied by z cross x2 minus x1 divided by the magnitude of x2 minus x1 squared. Now, let's call x2 minus x1 some new relative position vector y. So if our first vortex is over here and our second vortex is over there, then y is just going to look like x2 minus x1, which is this. All right, so this is a relative position vector of x2 with respect to x1. So I'm going to write where's the white chalk? Whatever. Blue is pretty dark. I'll go green. Can't really do any better. Okay. So we have d dt y is equal to what?
Baby, this chocolate is not visible.
Blue is even worse.
Is red. Blue is
Oh,
red.
red. I see. Okay. dy dt is equal to what? The sum of the circulations, or the field vortex strengths, multiplied by z cross y divided by the magnitude of y squared. Okay, now this is pretty nice. Here's something very special I'm going to do. I'm going to bring out our complex algebra skills. So let's call y, this is equivalent to saying, let's call z yx plus I yy, where of course I is just the square root of -1. So it's like we've transmitted
Maybe after this one, please go to the smart board.
Okay. It's like we've transmitted, this is y, x, y in the regular plane to y in the complex plane. Okay. So, we have this. dz dt is now equal to this. And what is this guy going to be exactly? Well, let's think about it. This constitutes what? Well, if z is over here, and meanwhile, y is busy lurking on the z is equal to 0 plane, if y is busy lurking on the z is equal to 0 plane, then, naturally, y cross z, or z cross y, it doesn't actually matter, I'm not bothering to use the right-hand rule right now, is going to be perpendicular to z, meaning it's also going to fall on this plane, and it's going to be perpendicular to y in this formation right here. So that means that it's just a rotation of 90 degrees in a particular direction. Now, in this case, since it's z cross y, what direction is it being rotated in? Well, this is transforming yx plus iyy into minus yy plus iyx. Or in other words, if this was y with yx and iyy, then this is what we are dealing with now. Iyx minus yy. A rotation of exactly 90 degrees. Okay. And that also corresponds to a multiplication by I. So this is equal to I multiplied by Z divided by the magnitude of Z squared. I should have added 2 pi a long time ago. Sorry. Now here's the kicker, right? If I dot y to both sides of the old equation, this is going to give me d dt of y dot y. This is equal to all of the blabber and then z cross y dot y. Z cross y has to be perpendicular to y by definition, and so the dot product of it with y has to be 0 by definition, which makes the whole thing 0, or in other words, the magnitude of y is constant. So that means that this distance, the relative distance, is never going to be changing. It's only going to be changing in terms of angle. So that means we can call this, well, sort of, an angular velocity, omega. We'll get more on that later. But for now, let me just call this, the magnitude of y, a new variable r. Actually, I don't know. So now we have dz dt is equal to this, iz over 2 pi r squared. Now, I guess I'll move to the smartboard because we don't have any more space. Here's what we do. We had dz dt is equal to the sum of the field strengths divided by 2 pi r squared multiplied by iz. So we're going to call this entire scalar right here the angular velocity, omega. So now, how do you solve this equation? Well, looks like dz is equal to z multiplied by a constant. So you introduce an ansatz. Z is equal to e to the rt. So dz dt is just equal to re to the rt. And well, it makes sense that r is equal to omega I. Hence, z is equal to e to the omega it, which is cosine omega t plus I sine omega t. So now, what does that tell us? Okay, so what this tells us is, well, it's not actually just this. Can you please stop saying that? It's not actually just this. It can also be multiplied by an amplitude that we know stays constant throughout the entire thing. It's just r, the radius. And so now, what does this tell us about y? Well, this is equal to yx plus iyy. See, the complex conversion wasn't for nothing, because now we know y is just equal to r cosine omega t, r sine omega t. Now, what does that actually tell us? Well, recall y is equal to x2 minus x1. Now recall that dy dt is equal to dx2 dt minus dx1 dt. Now recall that dx2 dt appears to be exactly circulation 2 over circulation 1 multiplied by a negative. So the negative, great. There we go. Okay, so that means I also have to erase my virtual mistakes, which means this gives us what? Well, now recall dx2 dt is equal to minus circulation 2 over circulation 1 dx1 dt, which means that dx2 dt minus dx1 dt is just minus circulation 2 over circulation 1 minus 1 dx1 dt, or minus circulation 1 plus circulation 2 over circulation 1 dx1 dt. So this could very well be y equals minus x1 plus some constant c. Now I'm going to bet, even though I actually haven't done the math in my head, that it's going to be something like Now, do I actually know that? No, I don't. I haven't done the math. That's just a guess, so to keep everything official, I'm going to write C. So what does that tell us? X1 is equal to y minus C multiplied by minus this. So C minus y multiplied by this. Okay, so that means that it's equal to, well, C minus y is just going to be C x minus r cosine omega t, cy minus r sine omega t, And then you multiply it by this. So you get minus, recall what r was. Well, actually, we don't have to recall what r was. It's constant. Multiplied by r, multiplied by cosine. Recall the value of omega, which is this. And then, comma, cy minus r gamma 2 minus gamma 1 over, over 2. Why does it erase everything? There we go. Okay. So, that's the entire expression. Can I even select that? No, that's impossible. Okay. So, this is the entire grand expression for the thing. And now, we can also find x2. x2 is what? x2 is y plus x1. Now, x1 is c minus 1 minus, no. Okay, so x2 is just x1 plus y, which is equal to minus y plus y, which gives which means you can have a slightly less crazy. Why is this on maximum thickness, man? It's a terrible idea. You can have a slightly less crazy expression that looks something like, what was up there again? Yeah.
Make it bigger. It's not visible.
Now?
It's invisible now.
Okay, so this is. Oh! Sorry. Cx minus y, which is equal to what? R cosine something or the other. I'm not even paying attention at this point. And then, comma, the same thing, cy minus sine. And that's how you close off your expression for x2. So, that's how you solve the case of 2-point vortices. I hope this was an informative video. Thank you everyone for watching, and we'll see you in the next one.